So let me move on to the idea of entropy in the context of the Carnot engine, the ideal gas Carnot engine that we are considering. So what I'll do is that I will introduce the notion of entropy, but discuss its ramifications in the next lecture. So we saw that if we have a, so suppose this is a PV diagram of an ideal gas. So we have P and there's V. And we saw in a previous lecture that, we have, these are the isotherms, right? So these are the isotherms. So what are isotherms? These are curves along which the temperature is constant. And then we also have, this won't be very accurate, but there are also, these are adiabats. Okay. So these are adiabats, meaning that these are the curves along which no heat is exchanged with the environment, right? So means that when a system, when a gas is being we are changing its state along an adiabat, that means that it's thermally isolated from the rest of the universe. Okay, and then so we can call these points, say, A, B, C, D. Okay. And we just learned that for the Carnot engine, the heat that is absorbed, say going from A to B, we can call it, say, QAB. And then there's a heat which is given up in going from, say, C to D. Let's call that QC of CD. We just, I just told you that QAB divided by QCD is equal to TAB divided by TCD. Okay, so T is a constant temperature along AB because it's an isotherm, right? So T is a constant temperature, whereas this is really the heat that is given up when you're going from A to B. So I can actually even write this as a delta, right? Because it's a specific amount of heat, right? It's a change. So so from here, what we can say is that we can write, say, delta of QAB divided by TAB minus delta of Q of CD divided by T of CD is equal to 0, right? I'm just reorganizing this equation. Now, suppose that we have, we take we adopt a convention in which, say, delta QI is positive if it is absorbed by the system, if it is absorbed by the system, and its delta QI is negative if it is given up by the system. Okay, so if I did this, then I can rewrite this equation as 1, 2. Let me call the first one then delta QI by Ti equal to 0, right? What I'm saying is, right, so I can, all the signs can be the same because I'm absorbing this minus sign into this thing, right? So now let's look at another Carnot cycle. Let's take a Carnot cycle that is, say, is something like this. So let this be, so it's in a Carnot cycle which is EB, and then this is FG, right? So here we have a smaller Carnot cycle, right? So for this smaller Carnot cycle, we can write an equation, and which is like delta of Q EB divided by, say, T EB plus, so this is basically, this part is basically going in this direction. On this direction, there is no heat, so there is no contribution, and then we have to go in the FG direction, right? So in the FG direction, it's delta Q F of G divided by T of FG. And because this is a Carnot cycle, this is equals to 0, right? Do you agree? Yes, sir. Okay. Now, the thing is that delta of Q of Fg is equal to minus delta of Q G of F. What does this mean? That means that if I were going, so here the Carnot cycle usually starts here, goes like this, right? It goes clockwise. But we could have gone counterclockwise, right? If I go when counterclockwise, then, when I go in this direction, I would be absorbing heat, right? And then I would be, when I go this direction, I would be dumping heat, and the work done would be done in the opposite direction. So we can write that delta of F of any amount of heat is equal to, if you are basically, here the indices mean that you're traversing in the opposite direction, right? That should be obvious. So now, let's look at our original Carnot cycle, which was going from A to B, B to C, C to D, D to A, and write that. So this is delta Q of AB divided by T of AB plus delta Q of CD divided by T of CD equals to 0. But then what we do is that we insert and subtract the same thing. And what we do is we add here delta Q EB divided by TEB, and plus delta Q FG divided by T of FG. Okay, I made a mistake, sorry. What I wanted here is delta Q AE, and I'm just going to tell you what this all means in a second. And so what I'm doing is, let me tell you what I'm doing. Yeah. So I have the first part, which is AB. I am dividing that into AE plus EB. Okay. So that's these two terms. Okay. And then what I'm doing is that I'm inserting this smaller, Carnot cycle, which is 0 here, because, I can always do that, right? So in the following way. So I insert this thing, and then I have to subtract this thing. So this will be delta of G, sorry, not G, delta of Q, and then here we have G of F by T FG, right? Because I'm introducing this thing, but this thing is just the opposite of this. So these two things will cancel out. And then we have, this thing as it is, plus delta Q CD by T of CD. All right. So then what I'm doing is that now I'm going to use this guy. So I'm now going to use this to say that this is 0. Okay. So what we have here are 3 of these things, and this is AE, this is GF, this is CD. What is this? Let's see. So this is essentially, if I go here, this is AE, and then go down here, there is no heat exchange. Then we have GF here. Then we are again absorbing heat. And then we are going down here, no heat is exchanged. And then we're going in this way, then heat is absorbed. And then, heat is given up. And then we are going up here. So what I've shown is that, if this is a Carnot cycle and this is a Carnot cycle, then, this quantity, this is also 0. Sorry, I should have said that this is 0. That, that any closed, so, if this is a closed path, okay, how should I need a notation for closed path. Okay, I'm going to invent a notation for closed path, okay? And the sum over a closed path this is going, as long as we're doing, a Carnot cycle, this is 0, right? That's what we have. We're going down isotherms and adiabats. This is basically going to be 0. Did you guys get that? What I'm trying to do?
Sir, in case of notations, T of FG and T of GF, are these the same?
They are the same, yes. Yeah.
But in terms of Q of GF and Q of FG are different. Reverse path.
Exactly. Very good. Yeah. Okay. So now if I look at a Carnot engine and look at any closed path, so I have any closed path on the PV diagram, I can always, infinitesimally, I can always express it in terms of, a sum of adiabats and isotherms, right? So for example, if I take this portion, I can just make it into some kind of zigzag, as long as the zigzags, are either adiabats or isotherms, right? So, and I can make that infinitesimally small. So this is where the physicist argument come in. Style of arguments come in, where instead of a mathematician. So at least intuitively, it should be clear that for a reversible engine, that the dq for a reversible engine divided by t for any path is equal to 0. Okay? Does that make sense?
Yes, sir.
And we saw that whenever we have some integral in which whose integral over some closed path was 0 meant that there must exist a quantity which only depends on the boundary value of that integral, right? And such functions are known as functions of state. So there must exist a function, there exists a function of state, say for the state S, let's call it SA for say state A, such that, we have some, say, reference state 0, and it's defined with reference to that state. Okay, so this is a function of the state, right? So if I have, so for every point on my PV diagram of the system, we have some, so this is A, this is B, this is C, this is D. There is a specific value for that state with reference to some, reference state. And this function of state is what we are calling entropy, okay? Now, the infinitesimal version of this is ds, and ds is going to be dq reversible over t. Now, we can use dq. Remember that our first law said that the energy, the change in energy, is equal to dq minus p dv, right? And therefore, we can now express our first law in terms of this new state function, which is t of ds minus p of dv. So this is the first law in terms of entropy, okay? Any question?
So what is the meaning of integration from 0 to a? Well, wouldn't we be completing a full circle?
No. So no, that's a good question. So basically, this is 0, and a is, say, suppose you take some path, and you end up at a. It has to be a reversible path. Okay. So it's just that, this is some reference. You can arbitrarily assign some entropy to it, say 0 entropy or something. And
Sir,
yeah.
could you comment on the path independence of this integral, that it will be path independent?
For as far as I understand, for the entropy to be defined in this way, it has to be, the path has to be reversible. What do you mean path independence? Okay. Otherwise, it would not be a function of the state, right?
Yeah, the
Yes.
function of states are always path independent.
Yeah.
Yeah, I wanted to understand why this is a function
Function
of
of
state.
states are path independent when you are considering paths which are reversible. There can be a system, and in fact, we will consider a system where, there are, say, paths from a point to another point, and this is a reversible path, and there's another path, irreversible, but when we're talking about difference in entropy, this is the reversible path that we use, okay?
Oh, okay.
So I think this is where all these thermodynamics become so become very subtle. Okay. But yeah, any more questions? This is confusing. You should have like a lot of questions. Okay. but we don't all we don't have to you don't have to ask all the questions right now, but I would like you to well, I will make you think about it. I will be assigning assignments, and I will make you think about it, and you will discuss this in the tutorial, and you will discuss it with me in the future. But you can also ask me questions now, okay? And you can ask me questions on the back channel chat. By the way, those of you who came late, there is a back channel chat whose link has been posted in the in Slack, okay? So
Mm.
if
So
you're
can you
shy,
give some?
yeah.
So can you give me some reference from where I can actually study about this topic from the book from the bundle?
Yeah, I use Blundell and David Tong for this, but there's another book which is very good, but it's a bit old-fashioned book, but it's a very good book. It's by I will link it in the website because I have an electronic version. It's by Pippard.
Okay.
Pippard, classical thermodynamics, and David actually does. He lists this book as a reference as well. And Pippard is amazing. He must be in his 90s, or he could be in his 100. I think he's still alive. So I used to know I used to know Pippard during my PhD days. He was a fellow of the college that I was a member of, and he's a very nice guy. But apparently, this is a very, very good book. Okay.
Okay, sir. Then
I will link it. Okay, I will link it to the
okay.
because I have an electronic version which I will illegally share with you.
Okay, sir.
Okay. Any more questions?
Sir, I had a problem related to the first tutorial problem. So we had to figure out the work done. So I was thinking, that was pretty straightforward. But I was thinking how we would figure out the efficiency of such a system that you
Okay.
provided.
Let me just finish off this topic, and then maybe. Unfortunately, I actually haven't had a chance to look at the tutorial problems yet. So I've been so busy. I farmed off the tutorial to Wasif the other day. That's a good thing for having a very good teaching assistant. But I will have a look at the tutorial and then get back to you. Is that okay, Nahi?
Yes, sir, thank you.
Yeah. You can also ask Wasif. He knows his stuff.
Oh,
Okay. Okay, let me, we have about 15 minutes. Well, we actually have 5, but I'll go above. Do you want me to stop here, or do you want me to press on and show you the second law of thermodynamics in terms of entropy today?